Okay. So now let us try to work out time independent Schrodinger equation. Okay. That is eigenvalue problem. Now to reach eigenvalue problem I need to do few things before, then I will try to solve time independent Schrodinger equation, which is eigenvalue problem. Okay. So time independent, so this becomes so this is same as eigenvalue problem. So I will state in terms of eigenvalue problem. Okay, you will see that how we get there. Okay. So before that I need to do some more work, how to solve nonlinear equations. So linear equations we will do later, that will be next week, but how to solve nonlinear equations. Okay. So I have to reach here, but before that I need to do this. So let us try to solve simple equation 1D fx equal to x. So we encounter this kind of equations very often, or well I will solve this kind of equations. Okay. So one problem was what was there in the exam. Okay. So iterative method. So how to solve it iteratively? So we start with some guess value x0, and next step what is x1? So put x0, f of x0 should be give you x1. So next one will be x1, which is same as f of x0. Then I get x1. So then this is x1 basically, x1. Then I go to f of x1. So that will give me x2, and continue till you converge. That is xn minus 1 mod must be less than epsilon. Okay, remember this was there in the exam. Okay, so this is how we solve this equation. But is there a guarantee that this will converge? Is there a guarantee? Will it converge always or no? So what is the condition that it will converge? Okay, so we can work out the condition when it will converge and when it will diverge. So let me just work out the condition, which is easy. So is the idea clear? So this is iterative procedure, we call it iterative procedure. So this just goes like that. Okay. So let us say that my answer is x star. There could be more than one x star, but I am close to that. I am going to, let us say that one of the solution is x star, and I start from a value near the x star. So imagine that I am starting with xn, so I will do for arbitrary xn. So I am looking at xn, so I want to see what is the xn minus x star. So this is error at nth interval, and relate this to xn plus 1 minus x star. So if this value mod is less than this, then you are converging. That is the idea. So what is xn plus 1 minus x star? This will be xn plus 1 is fxn by definition. And what is x star? X star is same as fx star, because that is a solution. Now since xn and x star are close by, I can do the derivative. I can do Taylor expansion. So Taylor expansion gives me, this Taylor expansion will be fx star plus xn minus x star f prime of at x star. I am expanding near x star, okay, and I drop the higher order terms. So plus higher order terms, drop it, minus fx star, and fx star x star cancels. So what do I get? So I get xn plus 1 minus x star is xn minus x star f prime x star. Okay. So, this is ignoring the higher order terms, which will work with if you are close to the solution. Now, if you are close to the solution, then now I know the condition. So, take the modulus both sides. If I am going to do it right here, take the mod. So, the condition of convergence that this must be less than this, right? That is a convergence condition, which is xn plus 1 minus x star divided by xn minus x star. This should be less than 1. This is error at n plus 1, this is error at n, this must be less than 1, implies okay. So, this is a stability condition. So, you have to know that derivative is less than 1, mod of derivative. So, there is a famous equation which is very fascinating equation, which is xn plus 1 is xn a, or I had put r 1 minus xn. So, these f of x n. So, what is it called? It is a quadratic map or logistic map. Or Feigenbaum map. It has many names, but these are. So, this has in fact we can compute the solution right away analytically. So, what are the analytical solutions? X star. So, just put so I want to look at for fx x equal to fx, x star equal to fx star. So, I am looking for a solution of the fixed point or the point where x equal to fx, and I am calling it x star. So, the solution is x star 1 minus x star. So, what are the solutions? Solution of this equation, easy to solve, no? One of them is 0, right. So, the solution is x star is 0, right, 0 0, and the other solution is 1 equal to r 1 minus x star, that is when x star is not equal to 0, then they cancel, and this implies, so this one equation, other equation will be x star equal to 1 minus 1 by r. So, there are two solutions. In fact, there is a nice graphical way to see this. So, this map looks like that, and this is a line y equal to x line. So, this is f of x and this is x. The solution is when f of x cuts x. So, how many places it cuts? It cuts here and here. So, these are two solutions, but of course, this solution is not valid for r less than 1. For r less than 1, it becomes negative, and so I am keeping myself to 0 to 1. Okay. I am doing bit fast, but if this is the case, there is only one solution. And if this is, I did not want to get into it, but I just want to illustrate how to find stability. So, let us imagine that I am in this regime, that there are two solutions. So, let us erase this. So, that implies that my r is greater than 1. So, there are two solutions, 0, and this is in fact 1 minus 1 by r. Okay. So, let us look at 0. Is it stable or unstable, by the way, right now? Is 0 a stable solution or unstable solution from the picture? What? Stable? How many you think is stable? Raise your hand, stable. So there was one vote stable. Unstable. Raise your hand. And third is don't care. I mean, stable. So don't care category, or I don't know. Fourth category. It's easy. The slope here is greater than 1. Slope 10-45 degrees is greater than 10-45 degrees. So slope is greater than 1. This is unstable. Okay, and this slope you have to see whether it is less than 1. Right now it looks like it's greater than 1, but for some values of r it is less than 1 and then it is stable. Now I can compute what is the condition. So let's see this equation. I have to just compute f prime x star. F prime x star. So take the derivative of this. So what is the derivative of this? R. So f of x will be just xn is replaced by x. So x minus x squared. Derivative is 1 minus 2x. Is that clear? So this is what derivative of f of x. Now plug in the value x star equal to 0. So f prime at 0 is r. For r less than 1, 0 is a stable fixed point or a stable point. So if I start this process, I will converge to 0. However, for r greater than 1, this is unstable. It will take you away from 0. In fact, this is going to take you away from 0 and bring you here until when? So let's figure it out. So now f prime of x star, which is 1 minus 1 by r. So I have to put the value of x star, this value. I am not doing very fancy algebra, okay. Feigenbaum, in fact this part was simple, because he did very complicated thing later, but this part was simple stuff, and I am not sure how many of you tried after the exam. So what the parameter given was stable for this fixed point, and we can figure it out for what values of r is stable. So let's put it here, r 1 minus 2, 1 minus 1 by r. That gives you r 1 minus 2 will give you minus 1 plus 1 by r, 2 by r. So that gives you minus r plus 2. Now I have to take the mod of this. So what is the band of r for which this mod will be less than 1? For what range of r modulus of this is less than 1? One to 3. Okay. From greater than 1 but less than 3, you can check yourself that for r between 1 and 3, this is a stable solution. Okay. And the exam, that was a value of r for which you are getting a fixed point. So for r just above 3, you jump around 2 values like this. So this is called period doubling. Okay. And so this system shows chaos. For r 3.6 it will show chaos. You can just compute, I mean this is simple stuff, you can just iterate it like this and you find that your xn will be chaotic. It will just jump between various values. Okay. Anyway, that is not my main point of discussion today, but this is how we solve x equal to fx. Now there is another way to solve x equal to fx. This is method 1. Method 2. Method 2 is called midpoint method. So suppose I have a solution like, I have f of x like this. So this is my root x star. So choose 2 points. Can it take few more minutes? Like I will just finish few of these, okay. They are very simple, but I will just finish it off, okay. So start with 2 values, x0 and x1, but you have to make sure that one of them is to the left and other one is to the right. You should be bracketing the fixed point or your solution, the root. This is also called root finding, so I am finding the root of this equation. So next time I am going to take the average of the two. So average is x2, which is x0 plus x1 by 2. Now x2 is here. So now I am getting closer to the fixed to my solution. So this will remain as left and this will go to the right. So now my bracket has, instead of this, it has become this. You have to keep checking that my solution is within error bound. I mean, you may not get x star completely, but you say, well, my f of x star is less than epsilon. After this, what do you do? Again I do the midpoint. My midpoint will be somewhere here. Now what is my bracket? Should I choose x0 and this one is bracket? No. So this is my x3, my bracket will be x3 and x2. So you should say left and right, and you have to choose one in the left and one in the right. So your new value is going to replace my left value now. Next time I do the mean, I will be here, I replace the right of them with this. So iterate this. So keep computing the midpoint, and midpoint will either be the next left or next right, and it will very quickly converge to the solution. So this is called midpoint method. This is straightforward, you have to just program it and you can get it. So I discussed 2 methods, one is iterative procedure and second is midpoint method. Okay. The Newton method I kind of quickly went through it. So let us just do it again. So if this is my function, then I want to find the root here. Then idea is, suppose you are here at this point, this x, then take the slope at that point x. Okay. So I am going to call it xn, and this will be xn plus 1. So you can see that this is closer to x star. So how do I find the value of xn plus 1? So from the property of slope, this is fxn. So f prime of xn, so I am finding the slope here, which is fxn divided by, sorry, this is n plus 1 is here, okay. So xn plus 1, xn minus xn plus 1. Right. So from here I can get xn plus 1 equal to xn, just bit of algebra, okay, xn divided by fx. So we iterate it, is faster, but you need to compute slope. Okay. Now there is a related scheme called secant scheme. In that scheme, so let me get it right. So you have 2 points and I want to get the next point, then in fact I want to use the same formula, but I can't get the slope. So I suppose I don't know how to find the slope. In fact we will see an example where I don't know how to find the slope. So the idea is you take a approximate slope by just choosing the 2 points. I can compute the value of the function, but not the slope. So this is my next point. So if I call it xn minus, let me call it xn. So this is xn yeah, xn minus 1, and this will be xn plus 1. So, this is a new value, fine. So, these were the old values. So, I start from xn minus 1, I go to xn, then from there I can get xn plus 1. So, how do I write the formula now? So, in fact, it is motivated from here. So, xn plus 1 equal to xn minus f prime. Did I make it a mirror? Prime is here. Dimensional also is wrong, no? Earlier equation dimensional is this correct now. So, f x n divided by f prime x n. But now f prime x n, I am going to use this slope, not exact slope. So, this will be written as x n minus f x n. So, function at x n, function at x n minus 1 x n. Okay. So, I need 2 points n minus 1 and n, and from that I can get x n plus 1. Okay. Now, these are the schemes we can use to solve, we can use them to solve nonlinear equations. So, I was trying to solve f x equal to x.